PhD supervisor in Mumbai University and have worked as a judge in different technical events in national and international level. He has been a technical judge, reviewer, editorial board member, and organizing committee member for national international conferences and journals of more than 38 such events. He has published more than 49 research articles and conference papers. He has delivered more than 25 expert lecture in FDP and short-term training programs and webinars. We welcome you, Dr. Sudhakar Umale sir, to the 1-week faculty development program on micro electromechanical systems. Sir will deliver the most important topic, that is the welding aspects in MEMS. Dr. Sudhakar Umale sir, continue sir. Hello sir.
I'm continuing, sir.
Okay, sir.
Does it come out of the presentation?
Yes, sir.
येत नाही मग बंद केला कॅमेरा.
Sir,
Share नाही होत.
now you can try, sir. Present now you can try.
Okay. Sharing, sir. Visible?
Yes, sir. It is about to visible. Yeah.
Now visible, sir.
Yes, sir. It is visible. Yes, sir. It is visible. Go ahead, sir. No problem.
Okay.
Sir, screen. Put in PowerPoint presentation mode.
Yes, visible now.
Yes, sir. It is visible. You can go ahead, sir. No problem. Visible.
So, good afternoon, all participants, organizers, coordinators, and my PG students who are working for this DP. So I am delivering particularly very typical topic, that is on welding metallurgy. Title: Effect of heat input on mechanical properties of weld and heat affected zone. Am I audible, sir? Clearly?
Yes, sir. Yes, sir. Yes, sir.
Okay.
Yes,
So
sir. You are
I will-
audible.
I'm
You're.
So it is the special topic on metallurgy and welding. To understand this topic, we require basic knowledge of heat transfer. Those who are teaching heat transfer, they can understand very well. Fluid mechanics, because we have the flow patterns in case of welding. Material science, to understand the properties of materials. Metallurgy. So these 4 topics we require to understand this topic, called as effect of heat input on mechanical properties of weld and heat affected zone. First, you understand what is welding and what is the concept of it. So I will give the little bit informations of welding definitions. Welding is a process in which permanent joint is produced by heating the material up to suitable temperature, with or without application of filler material and pressure. This is a very important definition. It has again second definition. Welding is a process in which materials of the same fundamental type or class are brought together and caused to join through formation of primary oblique secondary chemical bonds under the combined action of heat and pressure. So this is a very important uh, how to form the chemical bond during, if we get the correct chemical bond, we have a strong welding and welded joints. So we understand what is chemical bond. Next slides. Now, as it is connected with a special topic called as metallurgy, because we have so many changes in the metals before welding and after welding. You understand the changes in metallurgy, microstructures, mechanical properties, heat contained in the metals, heat contains in the welded pool, like that. So hence you must understand the metallurgy. Metallurgy is the science and technology of metals. It is based on the concepts from physics, chemistry, and crystallography. So generally metallurgy forms from three. We are learning physics, we are learning chemistry, we are learning crystallography in this topic. The metallurgy is the science that explores why metals behave the way they do. So behavioring of matter is very, very important. According to the behavioring of materials, we are selecting the materials for a particular purpose. This is very important, and it explains what is the importance of metallurgy for selecting the material. Now this metallurgy explains the properties, behavior, and internal structure of metals. These three are very important to understand the welding first. What is the property of base material? What is the property of electrodes? What are the behavioral changes? What are the internal structure? Like internal structure means microstructure, that is called as pages. It has, if it is ferrous materials, it is ferrites, pearlites, martensite, like that. Now, for the improvement of metallurgy, means for the improvement of welding portions, we require the special heat treatments to get the strength of the materials, and we require the different processes so that we can achieve the required material properties for specific applications. Now, what we really want, one really have to be familiar with different types of base materials and how they are affected by heating and cooling process in order to avoid weld defects. So we are producing the joints without any defects, and hence a process of heating you must understand, process of cooling we must understand, and we will discuss here what are the different heating processes, what are the cooling rates we are using during cooling of welding pools. Now a more complete understanding of metallurgical principles such as the relationship between the metals properties. We are keeping metals with metal properties and its chemical compositions. Every metal has its own chemical compositions. Functions of processes for weld, cold working, alloying, heat treatment. So you must understand what is cold working, what is alloying, what is heat treatments. Otherwise, this topic is very difficult to understand. This will allow us to have more awareness about the process and materials and take appropriate decision further. So a decision during welding is very, very important. Whether what type of electrode we require, what are the phase changes, we'll discuss one by one. Now you must understand the major types of welding processes are gas welding, arc welding, solid state welding, resistance welding, thermite welding, high energy beam welding, etc. We have so many types of weldings. Now, just to understand welding processes according to the subjects, many subjects we involve this welding process. Already I have given a hint for this heat transfer analysis. So we are doing the heat transfer analysis during welding processes, and because heat is transferred from one place to another, let us say from the source of heat. What is the source of heat? We have to decide first how it is transferred to the metal, what is the cooling rate, like that. What is the solidification rate, and hence first you must understand what is the heat transfer subject, which is a very core subject in the mechanical engineering. Without heat transfer subject, we cannot understand the welding process. Now, during welding, that is molten pool will flow from one place to another, and what is the rate of that molten metal flow, we have to calculate, and we are doing the calculations for welding process, and hence we must understand the fluid mechanics subject, so which require different dimensions numbers, and as you understand first fluid mechanics subjects. Now, during welding, we have different types of traces involvement. So some traces are developed after welding, and you must understand what are the stresses, and it can be found out by material science, and hence this subject is very important. Material science, you must understand what is material science, and this analysis can be done. Stress analysis I have not done in this seminar, but you must know what is a finite element analysis to calculate the traces developed during welding. And during welding, we have a lot of distortions. Distortion is undesirable conditions of the welding, and hence you must know what is distortion and what are the levels of distortions. Because of that, it is a particularly weld defects, and hence we must understand and how to calculate the distortion level, and hence you must understand the first material science again. So these are the third subject. This is the third subject you must know. Now, you must understand the next subject, that is a very important, metallurgical analysis. During welding process, we are doing the metallurgical analysis, means change in phases. Okay, when molten metal converts into the solid, it changes in different phases according to the temperatures, according to the chemical compositions, and hence you must understand this subject very well. That is called as the metallurgy. So, and again, this is a course. These are the fourth core subject in the mechanical engineering. And before starting of welding process, any welding process, you must know what is exactly welding design. And when you start any welding at any point, and it is very difficult to understand without any drawing, without any selection of materials, electrodes, flux, current, like that. And hence, to understand this, you must understand the very basic subject to understand, that is a welding process, that is manufacturing science. All five subjects are we are teaching to the different years to the students, and hence we have the five subjects. We will discuss all five subjects during our discussion. First, you understand the welding processes. What are the applications of it? So now we are doing the advanced welding processes, where a normal conventional welding process, non-conventional welding process, that is called as advanced welding process. So generally, welding process are used everywhere in the industries, starting from electronics, computers, laser fiber optics, nuclear technologies, electrifications, automobiles, radio and TV, high performance materials weldings, and many more applications. I cannot list out here. We have so many applications of welding processes, and you must understand what is exactly welding for different applications. Otherwise, if you don't know the applications, we cannot have the particular application. What is the pressure required for welding? Let us say electronics joining, computer joining, a nuclear technology we require, electrifications we require welding, automobile components we have to join for permanent joints, and hence we have to face so many problems. And what are the problems to be considered? I will discuss one by one. Now, what are the critical technologies in manufacturing? This is very important. So always mechanical engineering are facing a critical technology during manufacturing, and hence I have divided this critical technology in two groups, that is called as the construction industries. Okay, so you know what is the construction industries, where we are using the different welding processes. Manufacturing industries, we are using the different welding processes, and hence we are observing welding defects. Now we are concentrating on the welding defects. what are the welding defects available during welding, and what are the causes, why it offset, what are the source of defects, you have to find out. And hence it only if there is having lot of damages, lot of defects in the welding or welding joints, and hence it will destroy the industry, it will destroy the property also. If you are using any welding processes in the houses, in the industry buildings, and hence during the joining of machines, permanent joining, and hence these are destroying. But what is the loss if the welding defects are occur in the systems? That is the loss of human life. So this is very important to prevent the loss of human life because of small welding defects, and how to avoid it. So this is our aim, to find out the welding process clearly. And hence it is necessary to understand welding methods. Understanding of welding method is very important. Weld defects, you must understand. What are the weld defects? Heat generation during welding, we have to find out, and different problems during welding processes. These are very important. Now we are looking for that. 1, 2, 3, and 4. So when you solve the 4 problems, when you understand these, we don't have any problems in future. So we'll discuss one by one. And generally, as the title given by me, that is a heat input, effects of heat input on mechanical properties, on welded portion and heat affected portions. It is called as heat affected zone. And these are the two mechanisms we are following in the welding process. That is the melting of base metals or parent metals. And after getting a molten metal, then it is called as solidification. That is called as a cooling rate. So what is the cooling rate? What is the solidification rate? You have to concentrate. First you understand what is melting of the metal. Then you understand what is the cooling of the metal. First you understand solidification. Then it is introducing cooling rate. So cooling rate depends on the heat transfer rate. So you must understand what is the heat transfer rate from the surfaces. And hence these are the two steps involved in the welding, which is associated with the flow of heat. Okay, so flow of heat, which are depending on the rate of heat transfer in and around the weld metal. And hence what will happen because of these two, melting and solidification, we have the metallurgical structure of metal which is completely changed. Before welding, we have a different metallurgical structure. After welding, we have a different metallurgical structures, and hence strength of that welded joint may be changed. Complete hardness may be changed. Means we have a so many, even also some chemical composition may also change, and hence you have to find out what are the effects of metallurgical changes in the weld metal as well as in the heat affected zone, which is very close to the weld metal. And hence you must understand why we are understanding this subject. That is to understand what is the temperature. Okay, at every point we require the temperature. When the tip, nozzle tip or electrode is very close to the base metal, what is the temperature? When it is away from the temperature, what is temperature? What is the base metal temperature? What is the heat affected zone temperature? Like that. And you understand without distortion, without any problem, we have to select the proper cooling rate. And hence it is depending on the particular locations of heat affected zone and the weld metal. So we'll discuss later on what is the cooling rate. It is depending on time. Heat transfer rate. Heat transfer rate is depending on the time. When we have the graphs, like we'll discuss different graphs as time, as I get time, I will explain each and everything. This is A for A material, this is for B materials, this is for C materials. So we have temperatures. We are having different temperatures. We are interested in temperatures. at a particular time for different materials. And this is very difficult to understand. Hence, we must understand the basic equation of heat transfer. And welder has a very good practice of selecting the cooling rate for different materials. We'll discuss later on that, and hence we will concentrating only on the heat flow. We have so many mechanisms, but we will concentrating on heat flow in welding. For that, we have to understand. So I have written here, you must understand following changes during welding because of generation of heat. So what is the change we observe during this phase transformation? Okay, these are the different phases, ferrite, pearlite. These will changes after all. After welding, martensite may obtain, or any carbides may be obtained, or any phase change. Now, hence phase change will totally observed before welding and after welding. And we have to concentrate a change in resultant microstructure of the weld. And because of that microstructure, change in microstructures, we have to find out what is the property change before welding and after welding. And these now first we have to discuss second resultant microstructure, properties of the weld, and that gives the strength of the weld, base metal, weld metals, like that. And what is the third reason we have to discuss? That is residual stresses. This is a problem again. Suppose there are so many stresses developed in the weld material, and it is getting problems, and hence we have to find out. You are able to find out what are the residual traces, what are the distortions. It is again undesirable. This is an undesirable. This is undesirable conditions of the weld materials, and hence we have to find out. We are trying to reduce residual traces by selecting correct melting process, correct electrodes, correct base metals, correct temperature, and so on. So we'll discuss one by one how we reduce the residual traces and distortions in the materials. And hence what we are concentrating for reducing all these problems. And hence this heat flow in the weld is depending on different factors. So heat source, how the heat is generated, what is the quantity of heat generation, how the heat is transferred from one place to another. Okay, so it depends on thermal conductivity, thermal diffusivity, all mechanical properties of the material we require. Governing equations we are using generally for 2D equation, as well as we are using 3D equations. We'll discuss one by one. One 2D equation, 3D equations. Generally, it is practice because this welding process is so complicated, and for finding the governing equation, that is a heat flow equations, it is very difficult. But particularly, we have solved this equation in the heat transfer because of conduction. And hence, let us say we have a very thin material. We have a very thin material during welding. Then what will happen? We are selecting, preferably we are selecting a two-dimensional governing equation. Two-dimensional governing equation, because this is the depth. This is the depth here. As the material is very thin, we are considering 2D, means x direction. This is the x direction along the path of welding path, and this is x. This is the transverse path is called as perpendicular to x. This is y, and this is the z. But z quantity we are negligible here. Z direction is negligible because thickness is minimum. And so how this 3D governing equations we get? 3D governing equations we require when the object is base parent material is very thick like this. Then we are considering x direction this way, y direction this way, and z direction like this. And hence we got three-dimensional basic equation, and this three-dimensional and two-dimensional basic equation can be obtained by Fourier equations of conduction. You learn this equation from the heat transfer from third year mechanical engineering. This is the core subject for mechanical engineering. And as time permits me, I will explain the governing equation for 2D and 3D also. So we'll discuss one by one 2D and 3D. Heat transfer in the metal. Heat transfer in the metal. Let us say heat is generated at this point. Heat is transferred at a particular point. So it is transferred by conduction, and then you have to calculate what is the heat transfer. Let us say this is at one point, this is at second point. So ultimately, this is having more temperature, this is having less temperature, and hence temperature is very important, and hence heat transfer in the metal. You must know what is the procedure to calculate the heat transfer in the metal. Temperature directions. Temperature directions. So let us say this is a molten pool. It is also called as a weld pool, and at the center of it, it is a maximum temperature. Temperature is reducing. Here also temperature is reducing this direction, and hence now this is a molten pool, and this is a heat affected zone. So you must understand what is the temperature direction, what is the change in temperature directions. So let us say in the y direction, this is the temperature change direction, this is in the direction, this is the change in temperature directions. In the z direction, this is the change in temperature directions. Means temperature is lowering from higher value to a lower value, and it ends up at a particular point, and hence you must understand what is the temperature direction in the metals. Otherwise it is very difficult to find out stresses developed in the metal. And we have to select the direction of welding and heat flow. So generally direction of welding is taken like, suppose taken like this is the direction of welding. Then uh, this is the direction of welding. Direction of welding is very important, which decides velocity of welding or speed of welding. When I say it is a velocity, I use v for showing velocity. When I say speed of the weld, it is I am using s as a symbol. And even also cooling rate direction. So this is the heat transfer q, direction of heat flow. So this is the direction of heat flow, this is direction of heat flow in three directions. We will discuss third. Temperature at any point in the weld metal. You must be able to find out the any temperature. Let us say we find out, let us say this is a point, welding electrode. This is a welding electrode, and when you want to find out, we'll get the graph like this. Temperature graph with respect to the distance, and we are interested in the maximum temperature, and we are interested in the minimum temperature away from the electrode, and hence to understand the stresses and to understand any problems, to understand the cooling rate, so you must be able to calculate temperature at any point in the weld metal. And it is rate of heat transfer. Last is the rate of heat transfer q. So rate of heat transfer may be changed for different materials. We'll discuss one by one. And we discussed now heat input. What is the input? Input is giving to the weld. Now the heat is given to the weld, therefore it is heat input. And hence our main aim is heat input, which is the primary influencing factor for microstructures. Okay, as you change the heat input, definitely microstructure will change, definitely mechanical properties will change. And we are interested in mechanical properties because we want a tensile stress, we want yield strength, we want so many things, hardness, and hence our interest is mechanical properties of a weld. I am not talking about base metal, I am talking about weld materials. So what are the mechanical properties of weld metal after welding? So which directly depending on the available weld structures, and hence the heat input in welding process always is a great interest. So why it is to calculate exact heat input to the system? Because it influences the weld bead morphology. What is the weld bead morphology? Now let us say this is our weld surface, and here we are getting the pool like this. It is a solidified pool. It is called as a bead. And when you want to understand the mechanism of this bead formation, so it is called as a weld bead morphology. What is the morphology of bead formation? So what is the thickness of it? What is the this length? What is the height from the base metals? What are the contents of the bead means weld metal. Okay, what are the sizes of bed metals? It depends on this heat inputs. And fusion zone. Fusion zone is very connected to this, and heat affected zone. Outside, it is called as a heat affected zone. We have to discuss three things: bead morphology, fusion uh, zone, because in between that we have a fusion boundary. So fusion boundary is very important concept, and hence the boundary conditions. We are finding the boundary conditions for any change in heat transfer, thermal boundary layer conditions or velocity boundary layer conditions. We require the boundary conditions. Similarly here, we require the boundary conditions for the fusion, and hence it is called as a fusion boundary. We'll discuss what are the fusion boundaries, and hence we are interested in microstructure of these three. We'll discuss later on, and hence what is the source of heat input? What is the source of heat input? That is, the heat input can be referred to as the electrical energy supplied by the welding arc to the workpiece, and hence indirectly what we want to discuss, that is the electrical energy. What is the amount of current? What is the amount of voltage? And what time is required for conversion of this electrical energy into heat energy, that we are interested. Okay, so what is the melting point of the metal? That is very important. To calculate the electric current, we require the melting point. The melting point of metal is totally different for different materials. And what is the cooling rate after forming the welding arc? What is the welding arc? Welding arc is forming during the welding process. What is the rate of formation of welding arc? We have to discuss, and hence if the heat input is very proper, automatically we can have the correct electric current as well as correct electric voltage. We'll discuss electric current amount and electric voltage amount now, and hence we have to calculate what is the heat generation during welding. So heat welding. Now the let us say this is a heat source. Let us say it may be AC current, or it may be DC current, and this is the source we are using to generate. Now it is giving to the electrode, and here we have the metal. Here we have the metals, and hence now let us say we want to remove this metal. Now it is volume of this metal, and we have to add heat input to melt it. Okay, it is called as a volume of the metal, and what amount of electric current and what amount of voltage we require, that is very important, and hence we have to develop the equation for in mechanical way. We are converting this electrical way to mechanical way, and hence I am converting this equation as per the heat transfer, heat generation during welding, that is Q. And what is Q? Q can be calculated by two methods: heat required to melt at a given volume. This volume is this volume. So this volume can be melted, can be melt according to this uh, two way. Now this heat required to melt the solid. What is the melting? What is the heat required to melt the solid, and latent heat of fusion? So you know what is the latent heat of fusion? To get the latent heat of fusion, we have a different charts available in the market according to the material. So this is the formula. So in this way, I am able to calculate total heat required to melt the metal. So it is equal to Q equal to rho. Rho is the density of the materials. Rho, because I am calculating on the volume basis, kg per meter cube. Cp is the specific heat of material. This is the melting point of material. This is initial temperature of the materials, and this is the latent heat of fusion. This will obtain by the charts, from the charts. And hence we are interested, as you change the material, density will change, material melting point will change, Cp will change, and hence for different materials we have the different heat requirements for getting the weld pool. So these are the zones available. We are interested here. Now here we have the fusion zone. Here actual welding done. Here weld pool is formed. After fusion, it is called as fusion zone. So this is the boundary. This is the boundary. Now this is a very hot surface. After the fusion zone, this is again very hot surface. It is called as heat affected zone. In short, it is called as HAZ. HAZ. and this is the base metal which is unaffected by temperature. Okay, and hence we have to study the complete structure of fusion zone, the boundary of this boundary we have to discuss, this boundary we have to discuss, and affected base unaffected base material. Then you must understand before selection of the welding aspects, what are the welding aspects for different materials. So basic physical properties of the metals are very important. What are the physical properties? Because basically we are using the electric current, and hence electrical resistance. Now we are using the electrode. We are using the electrode. Let us say this is electrode. So we what electrode is doing now? The here in the electrode, electrical energy is converted into the heat energy. Why this heat energy is obtained? Because of the resistance of this electrode, and hence electrical resistivity. As this electrode has more resistance, we are getting the more heat energy. This is a simple way formula for that, and hence we are getting this heat energy from the electrical energy, and hence when we want any type of electrode which converts electrical energy into heat energy, so we are selecting the electrode in such a way that it has high electrical resistivity property. Particularly, this is very important in case of uh, gas metal arc welding. Gas metal arc welding. Here, melt is melting. Here, electrode is melting and producing energy, and molten metal of this electrode falls on the base metals. A second is having thermal conductivity, which is the basic property of the metal. Thermal conductivity, it is very useful. No, for the Fourier equation, it is equal to Q equal to minus Ka dt by dx in one dimensional equation. So this is very important for heat transfer, thermal conductivity, Ka dt by dx. And hence it decides this thermal conductivity. This thermal conductivity decides. Generally, what is the property of this thermal conductivity? Thermal conductivity is not constant at a particular direction. In all three directions, thermal conductivity change because of the uh, non-isotropic materials. Okay, we are selecting non-isotropic material. Generally, all materials are non-isotropic because phases contained like ferrite or different phases we are having in the metals. It is in not equally distributed, means material is not homogeneous. Therefore, we have a different thermal conductivity in all three directions. But when you observe uh, uh, materials, when we are selecting pure materials, it has the highest thermal conductivity. And when you are adding some alloying elements in that, the thermal conductivity will reduce. And hence you must understand, let us say you have very pure materials and you are adding silicon in there, manganese, then chromium, nickel, copper, then automatically thermal conductivity of that electrode will reduce. And hence for transformation of this, we are having the highest thermal conductivity of electrode. Okay, so basically thermal conductivity of electrode as well as thermal conductivity of base materials. Then this is the very important property, that is the coefficient of thermal expansion. So this is particularly may or may not be desirable. Okay, generally if you fix the two metals during joining, let us say this is one material, this is second materials, and this is a weld portion. Now after cooling, what will happen? Now the just you assume that this material is having very high coefficient of thermal expansion, it will trying to expand because of higher temperatures. And but these two metals are fixed during welding, then what will happen? So this material will change its shape, this direction. So this may be converted like this. So distortion means not having same shapes, or some cracks may be obtained, and hence during selection of materials, coefficient of thermal expansion is very important property. Now, what is the specific heat? Specific, you know that what is the, particularly it comes from the thermodynamics. When you learn or when you teach this subject, now this is the basic property in thermodynamics. It is a measure of ability of a body or a gas to absorb stored energy, because this is a very important. So when you add the heat, it should be stored in the body for some time up to the melting. And as the specific heat will increase, the melting rate will increase, because already we have known that mcp delta t, that is the internal energy depending on this delta t. Okay, so delta t is generally constant, m is constant, then cp will change. This cp will decide the energy contained in the body. Now this ionization potential is very important for welding. Ionization, what is the ionization? So ionizations are formed during arcing, welding arc. During producing the welding arc, so formation of welding arc, let us say this is electrode, this is electrode. Now this is during starting of the electrode, electric arc will generate. Now it is very difficult to generate the electric arc like this. Okay, if we are selecting the material in such a way that it initiates the maximum arc in short period, so that material may be selected, because it will take time, otherwise proper arc will not generate. We have the different size of the arc generation, so it gives the stability. Now this is, let us say this is arc. Now it is the covering area for that arc. Some arcs are very short, so this is the covering area. This covering area, that is the dimension from one end to another. This is very important for designing the weld, and hence this arc potential is important for selecting the materials. Metal oxides. Now this arc is a very high temperature, having very high temperature, and like, let us say this is a base material. This is a base material. It is a now it is in the melting. It is converting a solid into melt, and hence as it is having higher temperature. Now this metal will combine with the atmospheric oxygen and forming the metal oxides, and it is undesirable conditions. On the surfaces of this weld metal or base metal, we have the metal oxides, and if the oxygen rate is very high, then there is a problems in the welding, and hence we are getting the problems. That is and definitely this welding having some defects. Or because of that, because this metal oxides, what is another problem with this metal oxides? Let us say this is forming a very large thickness of metal oxides. Now when the heat is absorbing from the electrode to the arc, from the arc to the surface, it will not transfer to the inside, and hence it is insulation for, it is the insulation means the heat resistance will increase because of this metal oxides, and hence we are selecting the material in such a way that where there is less metal oxide formations, particularly when you select the aluminium. Now the aluminium has very sensitive to oxygen. When aluminium melts, it is very fastly combined with oxygen, atmospheric oxygen, and forming aluminium oxide Al2O3. And this Al2O3 is creating problems, and heat resistance is increasing, and hence it is undesirable conditions of metal oxides. Now this is very because we are using the electric current, and hence mechanical engineer will think about what is the efficiency of heat source efficiency. So generally, what is meant by heat source efficiency? So now the at the electrode, now this is a transformer. We are using this electric current I, then electric voltage. Let us say I am using E. I am using E, or sometimes I am also using V for voltage. Then V into I or E into I becomes voltage. Now is the wattage. Now this wattage energy will come when it comes to the surface. Is come to the surface. Now this heat is not completely transferred to the base metal. Heat will not transfer to the completely, and it has losses. Some heat will entered into the atmosphere, and we are interested what is the loss during transmission of this. So this loss must be calculated. So generally, in case of this which current you using, that is a AC current or DC current. So generally for AC current, we have a very less this heat source efficiency. In case of DC current, we have a large efficiency. Therefore, it is your choice how to select AC current or DC current. That depends on you. So we are interested in Q actual. So Q actual means the heat available at the base surface. Okay. Heat available at the base surface. That is the rate of heat transfer from the heat source to the workpiece. We are interested in that. Otherwise, because of this Q actual, we reach to the melting point of the metal. And what is Q nominal? Q nominal is the 100% energy giving by this transformer to the electrode, and hence it is called as nominal power of heat source. And this welding time is very important. How much time for welding? So it depends on the efficiency, and hence Q nominal then means this initial energy called as nominal heat is divided into two groups. First is called as heat transfer to the workpiece. Now heat transfer to the workpiece, that is the Q actual, and second is heat loss to the surroundings. And it is having heat loss to the surrounding is not useful for welding purpose, and hence we are trying to give some preventions for giving heat to the surrounding. So we will do preventions. So this is the formula, mechanical way how to find out the heat source efficiency. So as the heat transfer way, Q actual by Q nominal, and this is just I am multiplying Q actual into T weld, that is the time of welding, Q nominal T weld, and hence during in case of arc welding, so arc efficiency we are calling this heat source efficiency in case of arc welding called as arc efficiency. So that is the production of arc, and this arc efficiency we are converting this formula into Q actual here T weld, and here EI into T weld, and this is the formula for this is the total heat generation, this is the power by electric current, that is E is electric voltage, I is electric current. Just to find out his current must be always constant, therefore I have written here constant voltage, constant current. So during arc welding, this input is calculated like that. During so per unit length, we can calculate like that. Where when you calculate like this, the welding speed is very important. So what are the parameters responsible for heat source efficiency? Because we are reaching to the maximum, but we are not reaching. We can reach up to the, in case of DC voltage, we can reach up to the 85%. In case of DC voltage, we can reach to the 50%. And hence these parameters are very important. How to select the equipments for this the torch nozzle diameter. So generally in case of DC voltage, DC current, we are using the torch. Okay, so this is the torch. Now this torch is giving it has electrodes, this torch, and giving torch through this metal is added, and hence this diameter, nozzle diameter is very responsible. Okay, now welding speed, this welding piece, now this torch now moving with some velocity, so it is a welding speed. Material thickness is very important. As the according to the material thickness, we have the selection of we have the charts available in the markets. As the thickness changes, the current and voltage will change. And thermal conductivity of the workpiece, that is it. Now this is a high thermal conductivity material require lesser heat input, and higher lower thermal conductivity requires maximum heat inputs, because it has lower, because otherwise we get the we are not getting the homogeneous molten pool. So this we require. Now after this efficiency, heat source efficiency, next efficiency we require. Now we have reached to the base metal. We have now this is the base metal. So this base metal, let us say now the every energy is available. Now here it is available up to the arc efficiency. Now here we have the energy. We have the energy here. Because of this energy, and we are reaching to the melting point, and then when we reach the melting point, base metal will melt. Base metal will melt. This is the cross section. So what is exactly welder? Now this welder is interested in ability of the heat source to melt the base metal. Okay, as well as filler metal. Now both metals, base metal as well as filler metal, must be melt properly. That is our aim. and hence this efficiency is called as melting efficiency. And melting efficiency, it is written as eta m. So now I have taken the transfer cross section of the weld. Let us say after welding. So what is the contribution from metal, pillar metal? What material is deposited? What material is deposited here? This is very important. So this is the area covered by this. This is the outer surface area. This outer surface area is available for heat transfer. Now this is the called as a boundary. This is called as a boundary of the fusion weld. Now this is called as a fusion weld. This is called as a fusion weld. And hence this is the area. This is the surface area covered by the fusion. It is called as AB, base metal area, surface area. This is called as a pillar metal area. These two surfaces area are very important for contribution of melting, and hence we will discuss what is the contribution of pillar melt in case of increasing melting efficiency. What is the contribution of base metal for improving melting efficiency. Now this is the formula. This is the formula for efficiency of melting. So efficiency of melting depends on all these factors. I have written here AB. AB is already we have discussed. That is the area of base metal. V is the welding speed. T is the welding time. Welding speed. Welding time required for that. HB. HB is the energy required to raise unit volume of base metal. That is the heat energy which is required for metal melting. And this is another. This is for related to the filler metal. This is the area, surface area for filler metal. This is the welding speed, time for weld. This is the energy required for melting filler metal, and hence this is the now this is already we have forming. This is efficiency, heat source efficiency. This is heat source efficiency, and E into I, current voltage and time for weld. And in this way we are able to calculate melting efficiency. If melting efficiency is very less, particularly for DC welding, it is up to the maximum, up to the 85%, and it starts from 50%. Okay, 50 to 80%, and therefore DC welding, DC current may be selected to get the maximum efficiency, and AC is having generally up to 20% to 50% AC current, like that. So it may range by different conditions also. So that depends on the welder which current may be selected for getting this. And hence what is the effect of this melting efficiency on weld size? This how to select? Now this is a shallower weld. This is a shallower weld. So when the we have a very lower melting efficiency, just this thickness is a fusion weld or weld pool, the thickness is very less, and hence this thickness may affect strength of the welded joint or any problems we have. And hence just to observe that when we have a higher melting efficiency, now just you see the depth of penetration. It is called as generally a depth of penetration during heating, and this depth of penetration and after solidification, this is called as depth of fusion weld. This is very important, how much depth of fusion weld available for strength of the joint. So generally we are selecting the very high melting efficiency to get the strength of materials. And hence when you comments on these two figures, I have given some comments. Melting efficiency is lower because of lower heat inputs. Oh, so you have to select. If by chance you are giving lower heat input and welding speed lower, definitely we are having the lower efficiency. In second figure, what is happening? So melting efficiency is higher because of higher input and higher welding speed. So what is the conclusions on these two comments? It is concluded that melting efficiency cannot be increased indefinitely. So we have to obtain the correct melting efficiency. It should not be more or it should not be. Otherwise, metal will melt faster, and we have to increase by chance the welding speed. We have to increase the welding speed, and hence as the heat input rate will increase, definitely welding speed definitely we have to increase. Therefore, what is our conclusions? the power input must be increased along with the welding speeds. This is very important. It should be also be noted that in presence of surface active agent, this is very important. This is very important. In case of steel, surface active agent, it is called as surface active agent. What if the, you see, as if steel contains sulfur, by chance it is available, what will happen? What will happen if sulfur contains in this element? So it is very active element for welding. Sulfur is very active element. What is the activeness the sulfur is showing? It increases the melting efficiency, and automatically we get the formation of deeper weld like this. Depth is increasing. Depth is increasing. In case of non-metals or any other metals, we have titanium oxides, aluminum oxides, or any other materials we are using as a surface active agent that is required for metals as well as non-metals, and that improves the weld pool. So our aim is to increase the weld pool in such a way that each must be deeper to get the weld pool, deeper weld pool. Now, when we want some calculations, we are doing the, it is called as analytical calculations. We are doing analytical calculations for heat flow. So already when we are considering the heat directions, temperatures, and many other parameters, we have the 2D, two-dimensional heat transfer equation, three-dimensional heat transfer equations. These are used by the principles of Fourier equations. Okay, two-dimensional Fourier equations, three-dimensional Fourier equations, and hence during getting the heat or transferring the heat from the electrode to the base metal, we are assuming some assumptions. Otherwise, we are not getting the correct equations. It is very difficult to obtain the basic equations, and hence we are assuming the steady state heat flow, point heat source, negligible heat fusion, constant thermal properties, no heat losses from the workpiece, no convection in the weld pool. So by assuming, if I know that this is not possible, okay, constant thermal properties, if the material is heating, we don't say that it is having constant thermal properties, because thermal property will change definitely. Heat is leaving to the atmosphere from the workpiece. No convection is there. It is not only conduction, but we are assuming that no convection in the weld pool. So I am doing one, I have done one case study, and I will explain my case studies, which is done one of the industries. For I have developed this case study for the shipbuilding materials. Bigger ships are using low alloy this. So this is a very particular material. This is very particular material, high strength, low alloy steel grades of structural steels. So this is very costly material which are used for generation of or formation of pressure vessels, naval vessels, or compressors, air compressors. It contains very low carbon percentage, or alloying elements are very less, and hence what is the advantage of it? It has because carbon percentage. What is this carbon? Carbon is called as a austenite stabilizer. Okay, carbon is called as, when it is available, very high carbon is available, then if that material is not suitable for welding. And because why it is not suitable for welding? Because carbon is called as austenite stabilizer, and hence austenite is not suitable for our weld metal. It should be converted into the desirable microstructures, and hence we are selecting very costly material, that is high strength and low alloys grades of structural steel, which is having the very important property, that is the weldability. Okay, as we are using for marine purpose, and this material is very suitable for weldability. This is the weldability property. So because of this carbon percentage, and hence I have used this material as a shipbuilding materials. I have done some experiments on it. I want to show it, and hence what I have done in the whole experimentations, I have controlled the heat input. I have controlled the heat input during that period. control, how to control the heat input, to control the cooling rates, to control the microstructure, to control the mechanical properties. And hence we will discuss one by one. And hence what I did in my experimentation, change in microstructure directly affects the mechanical property. This is I want to change microstructure. This is my study. And this microstructure of the weld cooled metals depends mostly on the important factors like heat input, cooling rates, and weld metal chemical compositions. During that period, I have concentrated on weld input, cooling rate, and chemical composition of the this. And optimal combination of strength and toughness of this weld metal could be obtained by the formation of acicular ferrite. So what is this acicular ferrite microstructures? So this is a ferrite. It is a particular ferrite. Ferrite is obtained at a very low carbon percentage, and this ferrite is in the form of a needle structure. Okay, this is a needle. So this is needle structure, and this ferrite is in form of a needle structure. Whenever we get the needle ferrite structure in the metal, then we get the highest strength, and which is the desired microstructure, and that is my objective to obtain the shipping welding. And hence, now onwards, I am having the basic moderate cooling rate. This is my second aim, how to obtain the moderate cooling rate during welding. And this moderate cooling rate, so what will happen? Generally, we know that TTT diagram. So during the TTT diagram, time, temperature, and these transformations. So there is a formation of perlite, fine perlite, coarse perlite, benetic formations, benetic. No, it is generally formed in the benetic structure is formed in the steels. So we let us say we have the very faster cooling rate. So sometimes there is a formation of, let us say, this is my cooling rate. This is a TTT diagram. So sometimes we are getting the fine structure. Now this is the cooling rate, right, like that. So I am getting definitely perlite. I do not want perlite. So let us say I want this. No, what will happen if it is a faster cooling rate? Definitely, I am getting the martensite structure. I do not want martensite structure in the microstructure in the base metal, because the base weld pool becomes so hard, and I cannot do the machining later on. And hence, I am trying to get the very suitable material which has higher ductility. I want a very ductile material, and ductile material gives because of acicular ferrite. And we will concentrate on these three. And then just I will explain the what is the microstructures. So during this formation, during this conversion from molten metal to the, I have not that microstructure here. During formation of this, what type of microstructures I get? One is that major microstructure is acicular ferrite, which is desirable. Some boundary ferrites I get. Boundary ferrite I get. Some side side plate ferrite I get. Some polygonal ferrite I get. And majority is acicular ferrite in the weld regions, and it depends on the cooling rates. So this is the first conditions. Therefore, balance of cooling rate is very important. So to get the correct acicular ferrite, that depends on the heat inputs and better cooling rate, and how to transform this weld materials up to the desirable microstructures. I will have the study of this. Then value of welding current. I will select what is my welding current. Okay, so I select the welding current for a particular. I am using generally for this type of welded joint. Generally, DC current is selected. So welding current, this is I is selected. So what is the I? It increases the filling of molten metal. So this is the very important. As you increase the I, we'll get the more strongest molten metal, more molten metal in the that groove, and hence that is called as a weld nugget. Let us say this is a groove of weld metals. I am having more metal here. I had more metal here because of this higher welding currents. And what is the formation here? That is called as a bead. This bead shape is very important, and hence formation of bead is totally depends on the voltage, welding voltage, speed, and welding current. And hence, I have to control three things during welding: welding voltage, welding current, welding speed. And hence, generally, what is the welding currents I am selecting? Generally, it is approximately 2.5 times greater than weld penetrations or voltage and speed. So generally, we will select this. Just to observe that welding current and voltage is the main welding parameters for my study. Okay, welding current and voltage are parameters for my studies to get the correct heat inputs. And now, so I have selected high strength low alloy structural steels as a base material. This is a very specific, and I have selected this copper alloy wire. No, I have selected a wire as a metal for now it will melt. So copper coated. It is this iron metal is coating with copper. Now what is the just this is a very thin wire, and what is the diameter of this wire? This wire is having diameter 1.2 mm diameter used as the electrode. Now we will discuss the what are the problems, what are the advantages of this electrode. As just you observe that a low hydrogen content type electrode filler material is reduce the weld cracking. So let us say hydrogen, if the weld metal consists of hydrogen, by chance hydrogen is added, hydrogen it is added in the weld material, we have the very slow cracking. So this slow cracking is called as hydrogen cracking. Okay, and hence we are taking care of that. So zero hydrogen is added into the system. If some hydrogen is added, definitely you are getting the slow crack. It is not visible to the welding, but definitely there is a cracking that is called as hydrogen cracking, and our aim is to reduce the hydrogen cracking and which reduces the strength of the welded joint. Now, what is the benefits of copper as a coating? So this has benefits, as it is a base metal. Electrode metal is a ferrous metal, and why copper is using? Because of this property. We are increasing the better thermal conductivity, so that the heat can be transferred very fast and melting rate will increase. And hence, what are the advantages of copper and what are the advantages of high thermal conductivity? So I get the better arc. As the formation arc, no, this is the arc. This formation size of the arc is very important for this electrode hole, and hence that is the first reason. Longer contact tip length, So this is the length, contact tip length. This is the dimension. So I want this. The addition of copper in the weld metal improves the resistance to atmospheric corrosions. So we are forming the one layer on the surface, and this layer will create some atmosphere in such a way that atmospheric nitrogen, atmospheric oxygen will not touch to the surfaces and will not forming the oxides, and hence corrosion will not observing during this process. And hence, what is my shielding gas? No, generally shielding gas is necessary. Now, what are the problems? What are the problems is that now let us you assume that problems are the now let us this is a oxygen is adding. This oxygen addition in the weld metal is very dangerous. Nitrogen, because air contains oxygen as well as nitrogen. Okay, these three elements are very dangerous for weld metal. What are they? Generally hydrogen is not available, but it comes from the weld metals, it comes from any other source. It comes from the fluxes also. Electrode has some fluxes. It comes from the fluxes or electrodes. Nitrogen is available in the air, oxygen is available in the air. Therefore, shielding is essential. Shielding of the arc is essential, and if nitrogen is available in the arc, that creates the cracks. Oxygen is available, that creates the cracks or many other problems. And hence, we are using this mixture. We are using this mixture as the shielding gas. We are using shielding gas. That is a protection for the arc. 80% argon and 20% CO2. CO2 is used because it is available very easily. At 80, argon is not available, and hence But particularly if you keep 100% argon, no problem. But to make the economical conditions, we are using 20% CO2. The production cost will reduce. And generally, this type of electric current, because of this electric current, what is the nature of temperature? What is the nature of temperature? 2500 to 2600 temperature will obtained by this arm. Just to imagine what is the temperature. So this temperature is very essential, and hence that amount of arc should be generated. Now, what is the disadvantage during this process? If you are using the maximum temperature more than 3000 degrees centigrade by chance, we get. Now, what is the dissociation? This CO2 will absorb the heat from the arc, and it is dissociating into the carbon monoxide and oxygen. You take care of it. If you confirm that the welding temperature should not raise beyond to 3000 degrees centigrade, if it is that, don't select the CO2 as a shielding gas. Otherwise, this shielding gas is creating problem in the weld metal. So this CO2 is taking some energy, absorbing some energy, and it is dissociating into two elements, components, that is called as carbon monoxide. If this generation of carbon monoxide, it is harmful for that welder. So the welder is very near to the welding procedure, and it creates the problems for welder as well as material. This oxygen creates the cracks, and hence it is very essential what is the materials. So chemical reaction takes place. Chemical reaction takes place for why we require the chemical reaction. You understand this. I will take very fast. Structural changes we have by chemical reaction. So we have so many chemical reactions after heating. This is our aim: chemical reaction, occur filing joining with two similar and dissimilar metals. Our aim is to obtain the good weld quality. This weld quality depends on welding metallurgy. That is our different parameters. Selection of proper shielding medium. I have selected it. Suitable welding process. I have selected it, so that it reduces the residual stress generations and distortion. I am selecting always zero residual stresses. Zero. This is zero. Then I will select only that welding. Solidification mode. What is my solidification mode? Because of this solidification mode, microstructure will change. What is my microstructure for this? I want exactly acicular ferrite. Then it is my final microstructure which gives the maximum strength. Then this acicular ferrite will give the maximum mechanical strength. This is the chemical reactions can be controlled by using proper shielding gas. Now, generally, what will happen? This base material we have selected is again unclean. It contains some dust. It contains some oil. It contains some any other particles, fluxes. If it, let us say by chance a base material has oil, and this oil contains generally diesel oil or any other oil, lubricating oil. So this oil contains hydrocarbons. Now during welding, this hydrocarbon is converted into hydrogen and carbon separately. Carbon will burn, and this during hydrogen will evolve from this, and it is entering into the welding materials, and that gets the problem. And hydrogen cracking may be possible. And sometimes what will happen in the electrode? In the electrode has some or in the flux or on the flux or in the flux or in the on the surface of electrode we have some unclean material that creates the problems, and hence chemical reactions finally affects the weld metal compositions and mechanical properties. And hence you select the chemical composition in such a way that it gives the proper welding. And hence we have two problems. That is the gas metal reaction. Second is the slag metal reactions. So gas metal is shielding gas metal problem. Slag is available on the electrode. We have the two proper reactions. So I have selected what is this is the welding plate. Now this is a direction of welding. I have done this welding for my work. Now this is the voltage. In case of DC current, voltage is very less. This is a 22 is the voltage, 230 is the electric current. That is And now this, just you observe that this is the bead formation for this very thin bead formations we have. This is direction of welding. When we select 26 voltage and 260 current, just you for observe that as you increasing the electric current, the bead formation is stronger. The bead formation is stronger. Now this is the voltage 28. This is the welding current 280. Just you for observe that this is the electric. Now this is the formation of bead thickness. So now you have to select. You have to select the current and voltage in such a way that that bead formation must be suitable to you to get the strength of the weld. Now this is the, I will take faster. Now this electrode selections. I have selected this. Now this is the machine, automatic machines we are selecting. So this is a very new advanced technology. We are not doing manually. We are doing with machines. So what is the provision in the machines? We have the speed. We have the advantages of speed selection. Generally, we are selecting speed for this operation as 600 to 650 mm per minute. So this I select the speed here. Now I will give the command to this 600 to 650 mm per minute for this operation. Generally, this is the suitable welding speed. Now automatically machine will take the speed. Now this is the welding torch. This welding torch is very important. According to the welding speed, welding torch will move. So this is one of the parameter how to select the welding torch. So that gives the materials. Now we get the, now this is the complete is the frame. This is the complete is the frame. Frame is moving with this, and these are the shielding gas cylinders. According to the need, argon is there or CO2 is there. According to that, we need a different shielding gas cylinders. Now, major thing is that how to select the base metal or parent metal compositions. Already I have given that this material, this selected, this marine material is having very low carbon material. Just to observe that when you select the iron carbon diagram, you are the mechanical engineer. Now this is iron carbon diagram, temperature versus carbon percentage here. So here in this range, we will get this range 0.08 to 0.2. Now this is a eutectoid. Here we are getting the pearlitic structure. Here we are getting the completely ferrite. And when we have the ferrite in the normal atmospheric temperature, that is room temperature, that is completely ferrite, and hence we are getting the ductility property. Just to observe that every alloying elements having very less compositions, and that is very desirable conditions for the marine operations. This is the conditions for welding wire. So you have to select the chemical composition for welding wire. Just you observe that welding wire is also the very low carbon, because carbon is having many difficult. As you increase the carbon percentage, it is of carbon is called as austenite stabilizer. Nitrogen is also called as austenite stabilizer. Now this is the welding procedure. You have to select the base metal size. I have done this experiment in Naval Metal Research NMRL Amarnath Thane. So I have selected electric current, voltage, and welding speed. That three parameters are very important to get the correct welding procedure. These are the microstructures. I have selected some heat input. Okay, this is by selecting. I have taken three trial there. I have, this is trial 1. I have taken 3 currents, 3 voltage, and 3 welding speed. During that period, this is my heat input 1.13 up to 1.24 kilojoule per mm. And during that period, this is my volume fraction of AF means acicular ferrite, and this is the magnification of microstructures, 200 macro magnifications. Just to observe that I am getting 60% of acicular ferrites. In this 100% microstructures, I am getting 60%. What is my aim? To get the 100% acicular ferrite, but it is not obtaining. It contains some microferrite, it contains so many microstructures. Perlite may present, martensite may present. Now just you observe that this is my second trial. I have changed my current, voltage, and speed. During that period, this is my input 1 point. This is larger, but I am getting there 75%. Now this is increasing. This is increasing larger than this. And just to observe that, so this needle-like structure I got, needle-like structure I got. Now just to observe in the third trial. So third trial I have got the more heat input, but again this is the lower, this is decreasing secular ferrite. And what is my aim? I am selecting. This is mine. This is because this is my parameters. Because I get this. These are my parameters for my. Why I have selected this, which is a very desirable conditions for the selection of that, because it contains highest acicular ferrite, which gives the very strong. It has more ductility, it has more tensile strength, more hardness, like that. And but it is not brittle. It has having ductile properties. When after welding, generally some welding becomes brittle conditions, but here because of acicular ferrite, so we have the very high impact strength. That is, the toughness will increase, and ductility as well as toughness will increase because of this acicular ferrite, and that is my minimum percentage of martensite we obtain. So this is my third condition. So acicular ferrite is also obtained. I have taken, so this is the base metal structure. I have taken the microstructure before welding. I have taken microstructure before welding. In that welding, I have observed perlite, I have observed ferrite. Okay. So perlite and ferrite. So if we have more ferrite, it means more ductility. If it contains much more perlite, means it gives the more strength, like that. So I have selected. Now it is a welded steel plate. After welding, what I got, the plate, that material I have get. So just to observe that, I have the acicular ferrite. This is acicular ferrite structure. Here acicular ferrite. This is acicular ferrite. This is carbon bound grain boundary ferrite. This is a grain boundary ferrite. This is a side plate ferrite. This side plate. This side plate ferrites. This is a polygonal ferrite. This is a polygonal ferrite. This is polygonal ferrite. And maximum, you observe that I have got the maximum patches of acicular ferrites, and that gives the, in welded joint I got the acicular ferrites. Therefore I have selected this as my input for getting the maximum acicular ferrite, that is 1.52 to 1.62. So already I have explained why we need the shielding gas for that, because the nitrogen is very dangerous, oxygen is dangerous for welding. So these elements should be avoided. If there is a chance of mixing nitrogen, oxygen, and hydrogen in the weld zone, it creates a lot of problems. These problems may be cracking, porosity, or we are not getting any soundness. That is now particularly effect of nitrogen. Nitrogen is very dangerous. Nitrogen is very dangerous, particularly when it is available in the steel. What will happen? It increases strength but reduces the toughness. But in marine marine materials, we require the more toughness, and hence we are using the nitrogen. We are not using nitrogen. More shielding process. Now, when using the austenitic or austenitic stainless steels, because of nitrogen, what is the problem? Ferrite will reduce, but we require the more ferrite. What is the problem with this nitrogen in the austenitic or duplex stainless steel? Solidification, cracking takes place, and it is a very dangerous cracking. It reduces the strength, and hence what is the next is that nitrogen is a austenite stabilizer for austenitic and duplex stainless steels. So this nitrogen is not converting available because we are heating this nitrogen, so complete metal up to the superheating materials. That is called as superheating temperature. That is called as superheating materials. So very high temperature than the melting point temperature. Then when cooling rate will reduce, this austenite will not convert to the aspirite, and hence strength will not get. So when we want to join titanium, when we want to use titanium, what is the problem? It reduces the ductility because of these nitrogens. Now, effect of oxygen. So when we are using steel, we are having these same problems. Acicular ferrite is promoted, uh, but it reduces the toughness. Aluminium, it forms the oxide because of oxygen. Aluminium is very sensitive for oxygen, and these oxides, aluminium Al2O3, is considered as inclusions, and this inclusion is very dangerous for welded joints. Titanium increases strength but reduces ductility. These are the problems. Hydrogen, in case of hydrogens, in case of steel, it is having hydrogen cracking. In case of aluminium, it forms the gas porosity and it reduces both strength and ductility. Now, hence, what is the problem? Already I have given this CO2. CO2 generally not used in case of this metal welding, gas metal arc welding, and because it is for higher temperature, it is converted to CO and oxygens. So these are my samples for testing. I have taken. This is for base metal. This is for base metal. This is for welded joint. So I have measured it. I got a very vicious. I have measured the hardness, micro hardness at the joint, um, and I got these results. I have micro hardness testers, Vickers hardness. I have measured. Uh, this is my impact specimens for measuring welded joints. Now I observe that when we want, we have so many progressive way. We can do the PhD, we can do MTech on this topic. This topic is very hard, very vast. Many more when many more participants require wants PhD on this topic. They can do. They can do the treatments. Now I have done treatments for from room temperature to the cryogenic. I have selected different samples for different temperatures. I have kept for different times. So I observed that whatever may be the carbides available, after welding, so it can be converted into the acicular ferrite by heat treatment process. Okay. So after welding, what is the chance? What is the advanced technology to improve the mechanical properties? That is called as the cryogenic heat treatment. And when you keep that welded material in the cryogenic temperature, that is minus 50 degrees centigrade for some time, what will happen? So this lath martensite is obtained. It contains sometimes lath martensite percentage is available in the welded zone as well as a heat affected zone, that can be converted into acicular ferrite by using the cryogenic heat treatment, and hence we are getting the maximum strength. Okay, I will stop here. Thank you very much. Thank you for patience listening. Thank you, coordinator, Dr. Kiran Bhore. Thank you.
Thank you, sir.
And
We will take some questions if there are any questions from the participants.
Sir, shall I ask one question to you, sir?
Please go ahead, sir.
Sudhakar ji, sir, what is meant by white layer in microstructure in the welding process?
yes,
How this white layer microstructure, it will be produced during welding?
no, during welding, during solidifications.
Yeah,
During
solidification. How this?
Very little amount of generally it is produced. Majority of the microstructure available is acicular ferrite and a little bit ferrite. Okay, so I have not counted the what is the amount exactly, because I have concentrated only on measurement of the acicular ferrites. A little bit generally. So it is a formation, one of the formations. I have not gone through the very different way on microstructure studies because I have concentrated on the acicular ferrites measurements only. I have the correlations with heat input with acicular ferrites and any other mechanical properties.
Sir, again, my one question is in the MEMS, when we are using the titanium, this blade, and here, what type of this welding joining process used in this microelectronic parts in this titanium material. When we are using this titanium material in the MEMS component, then what type of this
No,
welding?
I have not done thoroughly that titanium welding, because I have done a majority of the work on cast iron and steels. My area is cast iron and steels. I have not done this titanium weldings. But I get the, if you have any problems on titanium, I will search my theory and I will go to it, because it is very interesting. Titanium welding is a very advanced welding.
Yes, 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 yes. And MEMS component, what type of this micro weldings are used, sir?
Micro welding is very, very advanced weldings. I have not gone through that.
Yeah, during in MEMS, micro welding, is there any process?
So temperature is very, very important, macro temperatures. What is the correct material and what is the relation of that microstructure, and that temperature is important.
Which welding process used for the micro welding?
Generally, aluminiums, titaniums.
Okay, sir. Thank you, sir.
Okay, sir.
Any other questions from the participants? Okay, I thank Dr. Sudhakar Umale for this informative lecture on the welding. Already the test link is posted in the chat box and WhatsApp group and through the email also, so you can do the test examination. Test examination link will be open till 8 p.m. And you can view that particular test examination. Feedback link is also available. You can view the feedback also for this particular session. And the test link is also available in the chat box. You can view that.
Hello, sir. This is the Google form for the test and feedback.
Feedback is also given, sir, and the test link also given. Okay. Test link is just now posted. Feedback link is posted just above it. Okay.
Sir, V9 is the test link and 7 that is the feedback link. Okay, sir.
Yes, sir. Okay. Now, before closing down this last session, so I want to know some feedback from the participants. You can share about this FTP, so that will be good. So, anyone who can want to share their valuable feedback or their opinion, experience, what they have gone through in these 5 days, please go ahead. Yes, Chetan,
Yes,
Somali, sir. Yeah,
yes,
please.
sir. Good afternoon, everyone. And this is a first of its kind experience that I had with Atal training, and that is online FDP that was conducted by Dr. Kiran Bole and the team of SPCE. And it was a very good experience in learning, and overall in these 5 days, starting from Dr. Anantha Suresh to Sudhakar Umale sir, and many, all the experts were almost, I'm very timid to say that they were stalwarts in their field, but they are really stalwarts in their field of MEMS and nanotechnology and so on. And we were lucky and privileged enough that Kiran Bole sir and his team had taken lot of efforts and put in pains to contact and bring all these experts on one platform to enlighten us and give us knowledge and awareness on MEMS and recent advances and opportunities in MEMS and nanotechnology. Again, it was a very good experience. This is my fifth or sixth FDP. Somehow SPC is involved into. Earlier, I used to attend in physical form. Now it's in online form. Thank you. Thank you very much, Team SPC and Kiran Bole sir.
Thank you very much, sir.
Hello,
Any other feedback?
Shall I speak, sir?
Yes, sir. Sir. Yeah, Vishnu sir, please go ahead.
Yes,
Hello.
yes. On behalf of this All India Sri Shivaji Memorial Society, College of Engineering, Pune, I am Professor Vishnu Sono. Here I am giving the feedback. Here, All India Council Technical Education Training and Learning Academy Atal sponsored 1 week faculty development program on micro electromechanical systems during the 23rd to 27 November 2020. Sardar Patel College of Engineering, they have called these eminent and professional faculties from the all over the India, like the Indian Institute of Science Bangalore, Indian Institute of Technology Bombay, and here the eminent speakers like the Anand Suresh sir, Gandhi sir, Bhattacharya sir, Nitin Kale sir, and Suhas Mohite sir, my Prasanna Gandhi sir, Das sir, Pratap sir, Rukde madam, and Dude sir, and Dixit sir, and as well as the not the last but not least Sudhakar Umale sir. They have delivered the nice lecture and professional speech to us. The various types of this MEMS advanced and advanced roles of this mechanical design in micro electromechanical systems. I am very, very thankful to the Sardar Patel College of Engineering, all the organizers and the team members who have come this organized this program, and I got this opportunity, and I am very, very thankful, sir. Okay, sir. Thank you.
विष्णू सर
Yes,
Yes,
sir.
sir.
सरांसोबत
Yes, sir.
अगोदर आपलं बोलणं झालेलं आहे सर. विष्णू सरांसोबत माझं बोलणं झालेलं आहे.
Yes, sir. Yes,
कदाचित ते
sir.
मला
Yes, sir. Yes, sir. Yes, sir. Sudhakar, sir. Yes, sir.
Bhole, sir, can I?
Yes, yes, yes. Please go ahead.
I Bharat Kale, Assistant Professor at Dattamegi College of Engineering, Navi Mumbai, is very much thankful to Dr. Kiran Bhole, sir, the convener, and the co-convener, Professor Hasin Sheikh and Professor Sharad Walvi, and HOD, Dr. Sudhakar Umale, sir, Principal, sir, Dr. Murudi, sir, and the Sardar Patel College of Engineering, the team, and the Atal Academy for giving me this opportunity to share my views on this FDP on the MEMS. Actually, the convener, Dr. Kiran Bhole, sir, is very well organized this the fantastic event with the eminent speaker from the IITs, IIScs, and some foreign university. And during this pandemic situation, we got the opportunity to listen or to acquire the technical and the motivation session from the such respectable and the knowledgeable person. Our life is having the means up and down of the stresses, and in this stressful situation, the session like Art of Living conducted by Dr. Prasanna Gandhi, Gandhi sir, sorry, gives the great reliefs. So I congratulate Dr. Kiran Bhole sir for the successful completion of this FDP, and I'm also thankful to the participant for the patient sharing. I hope this you have enjoyed this FDP, and some participant may be interested to do research work in this means in this field MEMS. So this workshop will be very much helpful to you and me also. Thank you so much, sir. Over to you, sir.
Okay, thank you. Any other comments?
Yeah, sir. Shall I?
Yes, sir. Please go ahead.
Yeah. Good evening to everyone. This is Dr. Prathamesh Poddar from Rajiv Gandhi Institute of Technology. I'm working as assistant professor in Rajiv Gandhi. Basically, MEMS is not my area, but still I've attended this, and after attending this course, I came to know that we are surrounded by MEMS systems and components. So it was a nice journey, and all experts have enlightened, they have motivated me to work on this area now. So it is new new door opens for me. I'll work on this MEMS from like today onwards, and it was a wonderful learning for me. And all speakers are excellent. Like I have learned so many things related to MEMS. Thank you, sir. And it was a well organized FDP. Thank you, Kiran Bhole, sir.
Kiran sir, can I say something?
Yes, yes. Please go ahead, sir.
Yeah, this is Suhas Deshmukh, currently working in Government College of Engineering, Karad. I think I'm audible.
Yes, sir. You're audible. No problem. Go ahead.
So actually, Kiran is my one of the good friend, I can say, and we worked together in IIT when he was doing research and microstereolithography work. So we had so much of discussion on MEMS, nanotechnology, but the way when we started our work, it was in a kind of in a just to learn from the books, and from this we didn't received in such a knowledgeable people at in a single platform the way he has organized currently. And so all the people from ISC Bangalore to IIT Bombay, all the eminent personalities and all these faculties are stalwart, and most of the faculties have taught us what is the MEMS. And so this is what in a good opportunity to all of us, like me and as well as all the participants, and behalf of participants I can say it, okay, that each and everyone has enjoyed this every session. I could not able to attend all the sessions. I may miss one or two sessions. The reason is that I was involved in some other activities also. But the way he has organized all the faculties, it is very difficult to get the time from these people anytime. I mean, so that is basically a problem we face when we organize such type of an FDPs. Because if we find a difficulty, because that particular person should be available at that time and he should able to deliver the session, all these things comes. Even though having such a so much of complications, he has organized very well, and I'm very much thankful to the Kiran and his entire team, along with his HOD Sudhakar Umale sir. And at the end also, Sudhakar Umale sir has given a very nice platform for learning in welding technologies, which we may take it to the future for MEMS like in a micro welding kind of things. So thank you, Kiran. Thank you very much for organizing such a faculty development program and enlightening each and every one of all the participants. And anyway, all the sessions are available on YouTube, I think. And we again go on revising, and we can learn many things. Even we can be in touch with the faculties who have given an assigned nice session. Thank you. Thank you very much. So what
Thank
do
you,
you,
Suhas.
Kiran?
Yeah, thank you, Suhas. Any other participant want to share their thoughts?
Bhole sir, just Amol Mangrokar.
Okay. Please go ahead, Amul.
Good afternoon to everyone. I am Amol Mangrokar from Rajiv Gandhi Institute of Technology. So just I am very thankful to give my views on this Atal sponsored FDP program. So the resource person that this STP is from IIS Bangalore to the engineering college like COP. So they are very rich in knowledge and having very large experience, and they share the experience and their views on this MEMS technology, and particularly on the special topic that is biomems and name sensor, and along with the some fabrication techniques also. So I am very thankful to coordinator Dr. Kiran Bole and his team, and along with SPCE Department of Mechanical Engineering from all the participants. So thank you very much.
Thank you very much. So last, I want to thank you to all the participants of this particular program for patiently listening throughout this particular program.
So Kiran Bole sir.
Yes.
Hello, Kiran sir. Kiran sir.
Sir,
Yes,
good evening,
Hello,
sir.
Kiran
This
sir.
is Dr. Jagdish.
Dr.
Yeah,
Please.
yeah. Sir, actually, sir, the way you approached all participants from the beginning of the day, and by the way you alert all the aspirants who wish to participate in this particular FDAP is really great, sir. Every moment you alerted us, and I am particularly, I'm personally very much thankful to you, sir, because I have some many doubts regarding MEMS to use MEMS device for biosensors. Particularly, Soman Das sir lecture was really the particular presentation was really enlightened me like anything, because now I came to know how to use this MEMS device for bio applications, biomedical applications. So with and also I have personal discussion with you, sir, Kiran sir, and you welcome me. You
Yes,
invited me to.
Yeah, we can collaborate.
Yeah,
We can work.
you invited me for your lab personally. That is great. You are you are very. I am very much grateful to you, sir. Thanks for your offer. And this entire all sessions are very good, and we got good knowledge about the
this emerging field. Nowadays, we don't know what is happening in the IITs and NITs, which type of research is going on in India in this emerging field. With this particular FDP, we came to know that what is happening inside the walls, that is this premier institutions in India. So thank you so much, sir, for arranging such a great workshop, FDP. Thank you so much.
Hello, Kiran sir.
Yes,
Hello, Kiran
please,
sir.
yeah, please go ahead. Please go ahead. Yeah.
Thank you, sir. First of all, let me thank Dr. Kiran Bale for giving us an opportunity to attend this Atal-sponsored FTP. And I feel this program was well structured and organized in a very good way. And I think, including me, all the participants, I think, got an insight into MEMS technology and what are the different fabrication process that is used for fabricating MEMS sensors. And the highlight of the program was, I personally feel, we have actually got a very good idea how these MEMS sensors are used. Okay, in some of the systems that we generally use in our day-to-day life, like either in the case of mobile phone, laptops, or automobiles, etc. And in between, we had an interesting session on stress management, art of living, and power of meditation. Okay, from Dr. Prasanna Gandhi from IIT Mumbai. And Dr. Ravi Shankar, sir has actually defined the COVID in a different way and how we can convert negative things into positive thinking during this pandemic situation. And sir has also stressed to keep academic ego away from for better learning. Okay, I think this program is really useful for participants who are already doing research in this domain or who are planning to do research in this domain, or people who are teaching, okay, this particular subject either in the graduate or